Hey folks, this is the third video for 3.1, and I hope that this is the shortest video. We're exploring elastic potential energy, and I'm also going to introduce mechanical energy. And so elastic potential energy is our last specific type of energy for this unit, and so we're going to do all of energy with just three forms of energy. Elastic potential energy has the symbol US because S for spring, and E is for electric potential energy, so it was maybe taken. So we're going to use S for spring. It is energy stored by the force required to deform an elastic object. An elastic object is one that when you deform it, once you let go, it will return to its original arrangement. And there are three elastic objects that I tend to use, and there's really just like one that AP Physics 1 tends to use, and that is a spring. And so the spring is important because we already know that springs produce a variable force, so a force that increases as displacement increases, and so that makes like the energy unit a little bit more interesting. The ones that I use are rubber band, especially because you can like hold it on your thumb, you can pull it back and let go, and it flies across the room. That's a good like thought experiment for types of energy. And then a bow and arrow is a good one. It does not deform in the same way that a spring does, because it bends itself instead of compressing or stretching, but it's really good because you can imagine that you like draw the bow back and then release, and the elastic potential energy in the bow pushes the arrow. Plus, you tend to do archery in PE, and so maybe when you're doing the archery unit, you're thinking about energy conversions. Anyway, the elastic potential energy equation is US equals 1/2 K times delta X. Sorry, I'm messing up the delta X squared. So let me read that again. Elastic potential energy, US, equals 1/2 K times delta X squared. These are the same variables from the spring force equation. This is the this is the force constant of the object, of the spring, and this is the displacement of it. Now the spring, again, the reason why AP Physics 1 uses only springs for this is because of the vocab or the variables used for it are consistent with the spring force. But you can model rubber bands and bows and arrows using the same sorts of variables. So that's kind of it for elastic potential energy. I did want to stop and do the unit analysis for this because it's a little crazier. It's 1/2 K times delta X squared. So the units on there are going to be newtons per meter, which is the units for K, times meters squared, which those are the units for displacement squared. One of those meters cancels, so I'm left with Newton meters. All right, so we have newtons times meters. We'll see that again. A newton is defined as a kilogram meter per second squared, and this is newtons times meters, so it's all of that times meters. That's equal to kilogram meters squared per second squared, and that is equal to a joule. So again, all the units are consistent throughout this unit. Even though all the formulas are the same, the units are all joules. Mechanical energy is last. It gets the variable of a capital E because for us it is the most general type of energy. It is the total energy in a system due to both motion and orientation. Now, orientation is just like how are the things organized, right? So if it's a spring, is the spring stretched or not? If it's a ball, is it flying through the air? Is it at rest on the ground? That sort of thing. So how do the forces of gravity and spring forces play into that system? And so very simply, mechanical energy is equal to all of the kinetic energy in the system plus all of the potential energy in the system. Just notice that U does not have a subscript, and so you will need to consider both gravitational potential energy and elastic potential energy. And that is it for this video.